Good morning, everyone. It's time for section 6.5, which is on the fundamental theorem of algebra. The fundamental theorem of algebra is very quick. All it says is that every polynomial with complex coefficients of degree n has n complex roots. So what does that really mean? It means that the number of roots has to match the degree. So if you have a fifth degree polynomial, there need to be 5 complex roots. This does include repeated roots. So if you have a root like x minus 2 squared, that counts as 2 roots. Even though it's one number, it still counts as 2 roots. So the number of roots needs to match the degree. The only thing we're going to do in this lesson is practice. So we're going to walk through one big example of everything that we've learned so far. As we walk through this example, what I'd like you to do is try to work out everything by pausing the video, doing it yourself, and then starting the video and checking your work to see how you've done. So I am going to go ahead and get started. Remember, you pause, you try it, and then start the video back up. So the first thing we have to do is list the possible rational zeros. That is the factors of our constant term. So factors of 24, which are 1, 2, 3, 4, 6, 8, 12, and 24. There's a lot of them, over the factors of our leading coefficient, which is 3. So those are just 1 and 3. So our possible rational roots, so I'm going to just do every one of the factors of 24 divided by the factors of 3. 1 divided by 1, 1 divided by 3, 2 divided by 1, 2 divided by 3, 3 divided by 1. 3 divided by 3 is 1, and you don't have to list it twice, so we just move on. 4 divided by 1, 4 divided by 3, 6 divided by 1, 6 divided by 3 is 2, which we already have. 8 divided by 1, 8 divided by 3, 12 divided by 1, 12 divided by 3 is 4, which we already have. 24, and then 24 thirds is 8, which we already have. And then, of course, the other thing that we have to do when we're listing possible zeros is put a plus or minus in front of every single one of these, because every single one of these could be either positive or negative. Okay, so we've got our possible rational roots. Part B says to look at the graph to narrow down this list. So I've graphed this function in Desmos, and if we take a look at the graph, there's some obvious integer zeros. We've got one at -1, and then we have one at 3. There is another 0 somewhere between 0 and -1. Looks like it's somewhere further, like between -0.5 and -1. If we were to narrow it down a little bit, zooming in, you can kind of see that a little bit better. So there's -1, there's our 3, and then this 0, which I'm not going to click on because we're going to use our possible rational roots for that. All right, so zeros, we have possibles at x equals -1, x equals 3, and then something between -0.5 and -1. All right, so the next thing we need to do is synthetically divide out the integer roots and any of the possible rational roots that we think might actually be factors. So take a moment, see if you can do this, and then unpause and come back in. I'm going to start by dividing out the -1. So I list my coefficients going across. And I put a line, bring down the 3, multiply up, add down, multiply up, add down, multiply up, add down, multiply up. Let's see, what is that? 24, add down, -24, yep, and 0, and that's my remainder. Since I have another root to divide out, I'm not going to rewrite this in general form. I'm going to actually go ahead and continue dividing. Bring down the 3, multiply, add, multiply, add, multiply, add, multiply, add, and there's our next 0 divided out. So now let's take a look at those possible rational roots just to see which one might fall between -1/2 and -1. So I'm going to eliminate, that one's gone, goodbye, 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 goodbye. Goodbye, 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 goodbye. So the only one that's possible that would fit is -2/3, which means it has to be it. It's the only rational root we have between -1/2 and -1, unless that root is irrational, but we're going to try this -2/3. So -2/3, putting my line, bring down the 3, -2, 0, 0, 12, -8, 0, and it worked. All right, so we have just divided out all of our integer and possible rational roots. So far we have found actual roots at x equals -1, x equals 3, and x equals -2/3. What is left when we divide all of those out? What's left, remember we started with a 5th degree, divided out the -1 takes us to a 4th degree, divide out the 3 takes us to a 3rd degree, divide out the -2/3 takes us to a 2nd degree polynomial. So what we have left is actually 3x squared plus 0x plus 12. So this is the polynomial we end up with, that's a 12, if we divide all of those other zeros out. All right, it's time to find the rest of the roots. So we have our 3x squared plus 12 equals 0. So if we just solve this, subtract the 12 from both sides, divide by 3, we get x squared equals -4. Square root both sides, don't forget your plus or minus. So my x is plus or minus, and let's think about this. This is the square root of 4 times the square root of -1. Square root of 4 is 2. Square root of -1 is I. So now we have found our complex roots. Our x equals plus or minus 2i. All right, so let's list all of our roots that we have found for this function. So all of our roots, remember every single number is complex. Even if it's real, it's still complex. It's all under the umbrella of complex. So we have -1, 3, -2/3, -2i, and +2i. We have 5 roots. Now we're going to write the polynomial in factored form. So when we write the polynomial in factored form, I'm going to give it the name f of x because that's what it was called. So I have x plus 1, x minus 3, x plus 2/3, and then we have this plus or minus 2i. Normally we don't list off imaginary factors when we're listing in factored form. Typically we would list just that x squared plus 4 or the 3x squared plus 12. Either one of those would be fine. I'm going to go ahead and list these, x plus 2i and x minus 2i, but then I'm going to show you that for most of the time, if you're asked for all of your factors to contain real zeros or to have no imaginary components, then what we would do here is have that x squared plus 4, or and if you notice, this doesn't have a leading coefficient of 3, so you'd either want to put a 3 in front and multiply it, or you could rewrite this guy as 3x squared plus 12, or you could write this guy as 3x plus 2. This would give you the same 0, but it wouldn't have any fractions, which is kind of nice. This one is what we found when we used our division. So either one of those would be fine. Personally, I'm going to write it as x plus 1 times x minus 3 times 3x plus 2 times x squared plus 4. So your other option would just be to put a 3 in front right here so that we take that leading coefficient into account. And actually we'll have the same zeros, but now we'll have the same scaling factor as well, our dilation factor. All right. Last screen, did our answer follow the fundamental theorem of algebra? Yes. We had a 5th degree polynomial, and we had 5 complex zeros. So yes, it followed it. And that's your lesson. Go have a good day and good luck.